Hello friends, in today's video we're going to be learning about computing limits not with tables or graphs but algebraically using the direct substitution property. So what is the direct substitution property? Well, simply put, the direct substitution property says when you're doing the limit as x goes to a of some function, the very first thing you should try to do is plug x is equal to a into f of x. And when you plug x is equal to a in, one of three things is going to happen. The first case is the easiest case. If you plug it in and it exists, you actually just get a number like 2 or 3 or 4, that's the easiest case. That's actually just equal to your limit. All right, the second thing that can happen if you plug in is you get 0 on the top and 0 on the bottom, or 0 over 0, which is called an indeterminate form. And if you get this, it doesn't mean you don't have an answer. It means you need to simplify. Okay? Now, later on in calculus, you might learn to use L'Hopital's rule to do this, but for now, we're going to use algebra techniques. And the third thing that can happen is you plug in and you get a non-zero on the top, something like 3 or 4 or -2, but you get 0 on the bottom. And when you have this, you have an infinite limit. Now, that does not mean that your answer is equal to infinity. It means you're going to have to check what type of infinity it goes to, and we'll go through an example of that later on as well. All right, this technique will work on almost every type of function. It works for polynomials and rationals, trig functions, exponentials, logarithms, which is almost every type of function. The only place where you have to be careful is on piecewise breaks, number 1, and number 2, on boundaries of root functions and sometimes inverse trig functions if you see those in your limits. So when we do have a piecewise break or a boundary of a root function, we know that we have to be careful. And of course, we'll go through examples of those a little later on in the video. With that being said, let's dive into some examples that show you the techniques that you'll need to be successful in your calculus class. So here we have the limit as x goes to 2 of x squared plus 4 over x plus 2. And again, we don't want to jump off by simplifying or trying any algebra first. The first thing we want to do is just take this x goes to 2 and just plug it in. So we'll get 2 squared plus 4 over 2 plus 2. On the top, we end up with 8. On the bottom is 4. 8 divided by 4 is 2. And that's it. That's your answer. But a lot of students will try to simplify this first. In reality, you just want to plug it in. If you get a number like we did here, we're done. All right, so let's take a look at another one. This time we have the limit as x goes to 2 of x squared minus 4 over x minus 2. And again, the very first thing I want to do is plug in 2. We get 2 squared minus 4 on the top, 2 minus 2 on the bottom, and this ends up being 0 over 0. Now, 0 over 0, again, is called an indeterminate form, and it doesn't mean that the limit doesn't exist or it exists. We really don't know at this point. What we need to do is simplify our original function here. All right, so there are a number of ways to simplify, and we'll do examples of a bunch of them in this video. But for this one, all we need to do is factor the top. X plus 2 times x minus 2. X squared minus 4 is a difference of squares. And we have x minus 2 on the bottom. And we're doing the limit as x goes to 2. Now here, you can see these x minus 2's cancel. And if you really think about it, when you plug in x is equal to 2 into x minus 2, you end up with 0. So we've just canceled out our 0 over 0. And now what we want to do is just plug back in. So we have the limit as x goes to 2 for x plus 2. And now we can just do that simple plugging in. We get 2 plus 2, and again, an answer of 4. Let's dive into another one. Here we have the limit as x goes to 2 of x squared plus 4 over x minus 2. We're going to start with that same technique of just plugging in, direct substitution. We get 2 squared plus 4 over 2 minus 2, which is 8 over 0. And again, this is a non-zero over 0, and this is our third case. This tells us we have an infinite limit. Now, again, it doesn't mean that the answer is equal to infinity. It means that it goes to an infinity, plus or minus. And what we need to do now is split our limit into the left side and the right side and check what infinity it goes to, or maybe it goes to both of them. So we're going to do the limit as x goes to 2 from the left, and we're going to do the limit as x goes to 2 from the right of the same function, x squared plus 4 over x minus 2, x squared plus 4 over x minus 2. So how do I do these one-sided limits? Well, it's actually pretty straightforward. All we need to do is figure out what sign this goes to. We already know it goes to infinity, we just need to figure out which infinity. And the way we do that is we take a number, so for x going to 2 from the left, we take a number just to the left of 2, let's say 1.9, and we plug it in, and we just figure out the sign of this fraction. Well, if we plug it into the top, 1.9 squared plus 4, well, that's going to be positive. It's going to be pretty close to 8, which is positive. It's going to be a little bit less than it, but again, all I need is positive. On the bottom, 1.9 minus 2, it's negative 0.1, but I really don't care about that 0.1. I just care about it being negative. Okay, so overall, we have a positive divided by a negative, so this means it goes to a negative, and again, I already know it goes to infinity, so it goes to negative infinity. Now on the right side, we're going to do a very similar thing, except this time we're going to take a number just to the right of 2, say 2.1. Again, we're going to plug it in, 2.1 squared plus 4 over 2.1 minus 2. Now again, that top is going to be pretty close to 8, so whether it's bigger or smaller, it's going to be positive. And on the bottom, 2.1 minus 2 is positive. Again, it's positive 0.1, but you just care about the positive. So we got positive divided by positive, so we have positive infinity. So one side goes to negative infinity, one side goes to positive infinity. Overall, the limit doesn't exist. Remember, they would both have to go to positive infinity or both go to negative infinity for it to exist and go to that particular infinity. But in this case, since they go to different versions of infinity, positive and negative, overall the limit doesn't go to the same thing, so the limit doesn't exist. So now let's take a look at a piecewise function. So here I have a piecewise function. It's equal to x if x is less than 1. It's equal to x squared plus 4 if x is greater than negative 1 but less than positive 1. And it's equal to 2x plus 2 if x is greater than or equal to 1. And in this particular problem, I just want to do the limit as x goes to 3 of f of x. So the first thing we need to do on piecewise function is determine which part are we actually going to use. Now, when x goes to 3, remember, it doesn't actually reach 3, but we're plugging in numbers like 2.9 and 3.1, and we need to think which one of these functions we're going to use. Well, if we're plugging in 2.9 or 3.1, we would be using the bottom function since x is greater than or equal to 1. So once we've determined that, we can just do direct substitution on this particular problem and just plug in that value of 3. So we're going to get 2 times 3 plus 2, or 6 plus 2, or 8, and that's just a number, so we're done with this particular problem. Now where things get interesting with piecewise functions is when you start to approach a boundary point. So I have the same piecewise function, but now I'm going to x is equal to negative 1. And what a lot of students will do mistakenly on this is they'll look and they'll see that x is greater than or equal to negative 1, so I must use this middle function. But in reality, remember, you never actually reach negative 1. You are less than negative 1 and you're greater than negative 1. And if you're less than negative 1, so if you're approaching negative 1 from the left, well, now you're less than negative 1, so you'll be using the top function, x. But if you're bigger than negative 1, so you're approaching negative 1 from the right, well, now you're bigger than negative 1, so you'll be using the middle function, x squared plus 4. And now, once I've actually broken this down, now again I can use direct substitution and just plug in negative 1. So if you plug in negative 1 to x, you'll get negative 1. So the limit from the left goes to negative 1. And if you're from the right, you're going to plug it into x squared plus 4, so negative 1 squared plus 4, which is 5. So you approach this limit from the right side, you go to 5. And both those one-side limits exist, but overall, you go to two different values, so your limit does not exist. Let's try one more with this piecewise function. So here I'm doing the limit as x goes to 1 of f of x. Again, I want to ignore the fact that x is greater than or equal to 1. I don't want to just use that one. Again, the limit as x goes to 1 has a left side where x is less than 1. And if x is less than 1, we're going to use the middle function, x squared plus 4. And it has a right side. If x goes to 1 from the right, now x is greater than 1, and we're going to use the bottom function, 2x plus 2. And now again, all we're doing is plugging in. We don't have to plug in 1 minus, we just plug in 1. 1 squared plus 4 is 5. So from the left it goes to 5, and that limit exists. And from the right it goes to 2 times 1 plus 2, or 4. And the right-sided limit also exists. But overall, again, we get that same thing. They don't go to the same value, so this limit does not exist. Now, if they did go to the same answer, if they both went to 5, then we would say the limit's equal to 5. Or if they both went to 4, we would say the limit is equal to 4. But again, if the two sides go to two different values, then the limit overall doesn't exist. All right, let's take a look at another example. Here we have the limit as x goes to 0 of the square root of x. On the heart of this looks like a pretty easy problem because we can just plug in 0, we get the square root of 0, and the square root of 0 is 0. Now, unfortunately, that is not the correct answer because on this direct substitution, we need to be very, very careful when we're doing piecewise limits, as we did in the previous example, and also at the boundary points of functions, usually square roots, but this can also happen on inverse trig functions as well. And the reason for that is that remember that limits are two-sided, and if we approach 0 from the left and we approach 0 from the right, we should get the same answer. But on this one, as you approach it from the right, you plug in numbers like 0.1, 0.01, 0.001, we'll get square root of things that are getting closer and closer to 0. But on the left, you're plugging in negative numbers. You're doing square root of negative 0.1, square root of negative 0.01, and none of those values exist. These things don't exist. And when these two values don't line up, one side goes to 0 and one side doesn't exist, overall, they don't go to the same thing, so our answer is the limit does not exist. So again, we have to be careful when we're doing this direct substitution in really two places. Piecewise functions is number 1, and number 2 on the boundaries of root functions, or maybe the boundary of, say, an inverse trig function. So now let's take a look at some more examples of the 0 over 0 case. It's probably the most common one you're going to run into. And again, the first thing you want to do is you do want to plug this in. 3 squared minus 3 minus 6 is 0 on the top, and 2 times 3 minus 6 is 0 on the bottom. So this is the 0 over 0 case. And again, that means we want to simplify. So in this case, how do we simplify x squared minus x minus 6 over 2x minus 6? Well, those negative 6's do not cancel on the back. Instead, what we need to do is factor. So here we can factor x squared minus x minus 6 as x minus 3 over x plus 2. And in order for this technique to work, we need to have some cancellation happen. So on the bottom, 2x minus 6 doesn't cancel with any of these things, so I also need to notice that 2 can factor out of the bottom, and that will leave me with an x minus 3. And again, these x minus 3's are where you're getting that 0 over 0. Once I cancel those out, I can do the limit as x goes to 3, and I can just do direct substitution. So 3 plus 2 over 2, or 5/2. All right, let's take a look at another one, very similar. Here again, we're going to plug in, and when we do, we'll end up with 0 on the top and 0 on the bottom. Okay, so again, we're going to go into simplification. Now in this one, we can factor it if you're very clever on it, but here I'm going to do the foiling technique, where I'm going to take this 3 plus h squared, and I'm going to FOIL it out. So 3 plus h times 3 plus h is equal to 3 times 3 is 9, plus 3h, plus another 3h, so plus 6h, and then plus h squared, and that FOILs out the top. Now, when I do the limit as h goes to 0, the 3 plus h all squared becomes 9 plus 6h plus h squared minus 9 all over h. Okay, and you can see these 9's cancel. Okay. And now this h can cancel because it divides into each one of these terms. So it'll cancel from that one, and it'll cancel one of the h's from the h squared, and you'll end up with the limit as h goes to 0 of 6 plus h. And we don't have any more dividing by zeros anymore. We can just plug in. We get 6 plus 0, or just 6 for our answer on this particular problem. So now let's dive into a little bit more complicated example. So this one, we have the limit as x goes to 4 of the square root of x plus 5 minus 3 all over x minus 4. Again, what we want to do is start by plugging in, and when we plug in on the bottom, we'll get 4 minus 4 or 0. And when we plug in the top, we'll end up with the square root of 9 minus 3, which is also 0. Okay, so we're in the 0 over 0 case, and now we need to simplify. And for simplifying a root, what we want to do here is do a technique called rationalization. And rationalizing just involves multiplying by a conjugate. And when we're subtracting or adding terms, the conjugate simply changes the sign in between the two terms. So instead of the square root of x plus 5 minus 3, we're going to multiply by the square root of x plus 5 plus 3. And we're going to do that on the top and the bottom of the fraction so that we don't change it. All right, so we have the limit as x goes to 4. Okay, and why we choose the conjugate is that we purposely determined a difference of squares here. We made a difference of squares. So when we FOIL out the top, we're going to get the square root of x plus 5 times the square root of x plus 5, and that's just going to be x plus 5. Okay. Then when you do the O and the I in the FOIL, you'll get plus 3 square roots minus 3 square roots, and those two terms are just going to cancel. And then finally on the end, the L in the FOIL, you get minus 3 times positive 3, and you'll end up with minus 9. Now on the bottom, we actually want to leave it factored. We do not want to FOIL. A lot of students will FOIL this and then immediately regret that decision because then they have to factor it right back out. Okay, so we want to leave it as x minus 4 times the square root of x plus 5 plus 3 on this bottom. Again, we want this x minus 4 on the bottom to cancel, so we don't want to distribute it. And it's going to go away in just a second here if we do the limit as x goes to 4. On the top, we're going to get x plus 5 minus 9, or x minus 4. On the bottom, we'll get x minus 4 times the square root of x plus 5 plus 3. Okay. And then we can see these x minus 4s cancel. Now remember, when they cancel, it doesn't leave a 0 on the top or a blank on the top. It leaves a 1 on the top. Okay. Now once we've done all that, now we can just plug in. We're going to get 1 on the top, and the square root of 4 plus 5 plus 3, or the square root of 9 plus 3, or 3 plus 3. So on the bottom, we end up with 1/6. Okay? So overall, this limit goes to 1/6. So again, this is a technique called rationalization, and to do that, we're going to multiply by a conjugate. So let's dive into another complicated example, this one called complex fractions. That's when you have an addition of fractions or subtraction of fractions inside of another fraction. So here we have 1/2 plus 1 over x all over 2 plus x, and the limit is going to -2. Now again, we're going to start off the same exact way. We're just going to plug in. When we plug into the bottom, 2 plus -2 is 0. And when you plug in the top, you'll have 1/2 minus another half, so 0 on the top as well. Okay. Now the technique for simplifying a complex fraction, there are a couple different ways to do it, but the way that I like to do it is to multiply by these subdenominators. So we find the LCD of this little 2 and this x, and that is just 2x. And we're going to multiply that on the top and the bottom. Now, again, when I multiply it on the bottom, I want that 2 plus x to cancel. So I'm going to do the limit as x goes to -2, and on the bottom, I want this 2 plus x to go away, so I'm not going to distribute. I'm going to leave it 2 plus x times 2x. Don't distribute down here because we do want that 2 plus x to go away. Now on the top, this 2 plus x is going to distribute, and it's going to come over here to the 1/2, and it's going to land right on the top. You'll get 2x over 2, and you can see those little 2's go away. So we just end up with just x, so we no longer have a fraction. Okay. Now on the second part, the 2x is going to land on the top of this 1 over x, so we'll have 2x over x. And again, we'll see that these x's go away. So again, we got rid of our complex fraction. Now on the top, we have x plus 2. On the bottom, we have 2 plus x times 2x. Okay, and we can see that this x plus 2 and the 2 plus x, they're the same, so they cancel. Again, it doesn't leave you with a blank on the top, it leaves you with a 1. And now finally, we still need to do this limit as x goes to -2. And again, once we've done this simplification, the limit is just plugging in. We're going to get 1 over 2 times -2. Overall, we'll get an answer of -1/4. So now let's take a look at a limit involving an absolute value. So here we have the limit as x goes to 3 of 3x minus 9 over the absolute value of x minus 3. We start the same exact way. We plug in x is equal to 3. We get 3 times 3 minus 9, or 0 on the top. And 3 minus 3 is 0, and the absolute value of 0 is 0, so 0 on the bottom. So we need to simplify this. Now the question is, how do we simplify an absolute value? Well, the big thing is that absolute value is a piecewise function. So the absolute value of x minus 3, it's going to be equal to x minus 3 if x minus 3 is greater than or equal to 0, i.e. it's positive, okay? And x minus 3 is greater than or equal to 0 is the same thing as x is greater than or equal to 3. And it's going to be equal to negative of x minus 3 if x minus 3 is less than 0, if it's negative. Okay, so x is less than 3 in this case. Okay, so in reality, to simplify this, we need to think about which piece of this piecewise function we're using. And again, as we go to 3, that is the boundary point of where the definition of absolute value changes. Okay, so we need to actually use both. This is a piecewise function, and we need to break this up into the two different parts. So we need to look at it from the left. So as x goes to 3 from the left, well, the top will be 3x minus 9, but the bottom, x minus 3 inside of there is going to be negative, so it's going to come out to be negative x minus 3. Okay, as we approach it from the right, we'll do the limit as x goes to 3 from the right. We'll have 3x minus 9 on the top. But now the stuff inside the absolute value is going to be positive, so it's just going to spit out x minus 3. Okay, so how do we simplify this? Well, the top can factor in both cases. A 3 can factor out, so I'll just do it right here. You'll have 3 times x minus 3, okay, on both of them. Okay, and once I factor that out, we can see that 3 canceling from the top and the bottom on both of them. Okay, but these answers go to two different things. On the top one, as x goes to 3 from the left, we'll have 3 over negative 1, which is negative 3. And on the bottom one, as x goes to 3 from the right, we'll have 3 over positive 1, so positive 3. Okay, and again, remember when the two sides go to two different values, overall, we say that the limit does not exist. Finally, let's examine one more technique called the squeeze theorem. Now here, direct substitution doesn't quite work because if we plug in, we're going to get 0 to the 6 times sine of 3 over 0. And 0 to the 6 is just 0, but sine of 3 over 0, well, 3 over 0 is an infinite limit, and sine, as you go to infinity, well, it just goes up and down forever, so that limit doesn't exist. Okay? And 0 times doesn't exist. We really don't know what that does. That's not part of our little flow chart on how to do these limits. So what do we need to do here? We need to use the squeeze theorem. Now, why do I know the squeeze theorem? Well, because the squeeze theorem almost always has a term like this, either sine or cosine of something kind of complicated inside of it. And the reason for that is that we know that sine of whatever, doesn't matter if it's x or 3 over x, it's going to always be less than or equal to 1, and it's always going to be greater than or equal to negative 1. And this squeezes it in between two different functions, which we know pretty well. And now what we do is we just multiply all the parts by x to the 6th so that we can create the function that we're concerned about in the middle. We get x to the 6th sine of 3 over x. And in one case, that's less than or equal to 1 times x to the 6th, so x to the 6th. On the other hand, it's greater than negative x to the 6th. Okay? And now we can just compute this limit. We can do the limit as x goes to 0. Well, on the right side, as x goes to 0, x to the 6th goes to 0 to the 6th, or 0. And on the left side, as x goes to 0, negative x to the 6th goes to negative 0, which is always 0. So that means that the middle limit also has to go to 0. There's nowhere else for it to go. It's squeezed between two functions that go to 0, so it has to go to 0 by the squeeze theorem. So overall, this limit is just equal to 0. And as always, please take a moment to like this video and subscribe to my channel.